بسم الله الرحمن الرحيم. نبتدئ على بركة الله ورشة العمل الدولية التي يقيمها قسم الرياضيات. أود أن أوضح أن المحاضر هو محاضر أمريكي، ولهذا السبب سأقوم بالتحويل للغة الإنجليزية ليكون معنا في الصورة. شكرا للجميع. Ladies and gentlemen, it's my great honor and pleasure to welcome you all in our first international virtual workshop in mathematics. First of all, I would like to welcome our Dean, Professor Serwan Al-Janabi, the Dean of our faculty, and thank him for his coming. And also, I would like to thank our keynote speaker, Professor Dr. Roger Nelson. I'd also like to welcome our audience, all of you. I really feel honored that you are our audience, and I'm very proud that you have joined us. Of course, I really would like to thank Professor Serwan Al-Janabi, the Dean of our faculty, for his support and for introducing all the utilities that made us up to make this workshop real. Before I start, I will give a short CV about our keynote speaker, Professor Nelson. So if you allow me, please, to read a short CV about Professor Nelson. So Roger Nelson earned his bachelor degree in mathematics at DePaul University and his PhD in mathematics at Duke University. He is currently Professor Emeritus at Lewis and Clark College, and also he taught at Mount Holyoke College and the University of Massachusetts at Amherst. He is author and co-author of 170 research and expository papers and 14 books. His primary interests lie in the areas of visualization in mathematics and multivariate dependence modeling in statistics. He is a mathematician of the first degree and a statistician and at the second degree. Professor Nelson, please feel free to presentation, and you have the mic now.
Well, thank you very much, Professor Al-Abdali, and I want to thank you and your colleagues for the kind invitation to give this presentation, this virtual talk. This is I have to admit, as we start, this is the first time I've done this, and I think this is, maybe as a result of the current pandemic, will become much more common, and we'll get better at it with practice. But anyway, I certainly appreciate the opportunity to talk to you a little bit about copulas, what they are, and how I was introduced to them. So first of all, let me give a brief outline of the presentation. I want to begin with a dedication of the talk to the mathematician that I learned about copulas from, who was a real mentor to me. A little bit of my background as a mathematician. As Professor Al-Adili mentioned, I've been at Lewis and Clark for 51 years now, and tell you a little bit about my early years, and especially a sabbatical year that changed my life. I'll mention a couple of books. One is a book on metric spaces, probabilistic metric spaces. That's was the source where I first learned and studied copulas. I'll tell you sort of about the journey from metric spaces, the triangle inequality in metric spaces to copulas, how that occurred, and sort of the first appearance of the application of copulas in statistics, and then a little book that I wrote some years afterwards called An Introduction to Copulas. A little later on, I'll mention quasi-copulas. These are important functions. Every copula is a quasi-copula. They sort of, copulas live inside the space of quasi-copulas. And then I'll kind of conclude with some trivia about copulas, and when I think about some good news and some bad news, we'll sort of conclude the talk. So first of all, I'm going to dedicate this talk to my former colleague and mentor and very good friend, Bertold Schweitzer. He's greatly missed. He passed away about 10 years ago. And for many, many years, he was a professor at the University of Massachusetts in Amherst. And it was a real pleasure of mine to meet him when I spent that first sabbatical with him at the University of Massachusetts. So some background, maybe before I talk about this background, I should just give you an idea. Some of you may not be familiar with copulas at all, and just verbally tell you why I think they're important in statistics. And first of all, if you think about distribution functions of one variable and joint distributions for two variables, a bivariate distribution function can be coupled to its univariate margins, and that coupling function is a copula. So the copulas sort of join or couple univariate distribution functions to form bivariate ones, and can be expanded to the multivariate setting. And this they're important in statistics because they give us ways to construct bivariate and multivariate distribution functions, knowing what the univariate margins, what the one-dimensional distribution functions are. And that's probably enough about copulas to sort of understand, the journey that I took in learning about them. So anyway, some background that's on the slide in front of you now. As Professor Al-Adili mentioned in that short bio, I did my graduate work at Duke University. I wrote my dissertation on a topic in queuing theory. I'd studied stochastic processes, and I thought queues were interesting. And I got the degree, what's that, 51 years ago in 1969. And my first job, my only job, was started in the fall, in September of '69, here at Lewis and Clark College, which is a small, what we call liberal arts college. We have only undergraduate students. There's no master's program, no PhD program here. It's all the first 4 years of college or university for our students. They come to us, they're about 17 or 18 years old, and they leave when they're 21 or 22. And I had a wonderful undergraduate experience at DePauw University, and all the time I was in graduate school, my objective was to become a college teacher and to teach mathematics to undergraduate students. When I first came here 51 years ago, the research expectations were sort of minimal. I did not pursue additional work in queuing theory because the problem I worked on was sort of an isolated problem, and I was fortunate enough to solve the problem, but it didn't really lead anywhere. It didn't lead to further work. But during my first decade here, during the 1970s, the research expectations began to change. The colleges, of course, we would never be research universities, but we had there was an idea that we should be research colleges. And so during the 70s, that sort of picked up, and by the time the 80s began, and say the first academic year, 81, 82, at Lewis and Clark, I really wanted to get back into research. I really had to do it if I wanted to stay here and continue to produce. And I was eligible for a year-long sabbatical a couple of years later in 83, 84, and I wanted to put that to good use. What should I do? What should I study? Where should I go? And while I was thinking about that early on in 81, the academic year 81, 82, I received the following announcement. It was on yellow page. It was on yellow paper. This is what an announcement that would go on the department bulletin board would look like. It was done on a typewriter. There were no computers or anything like that at the time. And this one, it's rather small print, so let me read it to you. It says, the Department of Mathematics and Statistics of the University of Massachusetts at Amherst announces the availability of sabbatical lectureships. And so these were lectureships for people on sabbatical. It says these lectureships are open to faculty members of colleges and universities without PhD programs in mathematics or statistics who wish to spend their sabbatical leaves at the University of Massachusetts. Applicants should generally have at least a master's degree, usually required to teach one course per semester, and will be expected to enroll in 1 or 2 courses and a seminar. There were stipends that would pay for this with no tuition. It says, for further information, write Professor L.N. Mann, head of the department at Statistics. And so I wrote to Professor Mann, and the following February, I received this very nice letter from the University of Massachusetts. It's even harder to read. It's probably pretty small print. But it says, enclosed is the letter and enclosures that I usually send to persons inquiring about our sabbatical lectureship program. And the writer of the letter goes on to give me some more information about this. And please note the author of the letter. And if you can read below the signature, it says Bertold Schweitzer. That's the fellow to whom I was dedicating this talk. This was the first time I had any communications from Bert. I didn't know who he was, but I did apply in the fall of 82. I received the position, drove 5,000 kilometers across the United States to Massachusetts. I'm on the West Coast, on the Pacific Coast here in Oregon. Massachusetts is on the Atlantic coast. So it was an interesting, how long did it take me to drive? A couple of weeks, because I had to stop and see friends all the way across. But so I drove, getting there in the fall, late summer of 1983. And University of Massachusetts is often just called for short UMass. And at UMass, I learned I would teach a calculus course each semester, which was fine with me. I've been teaching calculus my entire life, I think. And then I could audit 2 graduate level courses in statistics each semester. And that was a real treat because I figured, I knew some stochastic processes. As a result, here at Lewis and Clark, I was teaching the probability and statistics courses. And I felt that to continue to do that, I should learn some measure theory and learn some non-parametric statistics and learn some reliability theory. And those are the kinds of courses then that I audited at UMass. But most importantly, before I even taught a first calculus course at UMass or went to one of those stat courses, I met Bert, that Professor Schweitzer, and I went to his office to introduce myself. He asked me about my interests. I mentioned statistics, and he handed me a copy of this book. And here's the cover of the book. And the title is Probabilistic Metric Spaces, and in small print below the title it says B. Schweitzer and A. Sklar. And A. Sklar is Abe Sklar. If you've done any work in the theory of copulas, you know of Sklar's theorem. It's the foundational theorem for the application of copulas in statistics. You might call it a fundamental theorem of copulas. And it's Abe Sklar published that without proof, by the way, in a 1959 paper in French. And so why did I get this book from Bert? He mentioned that I might enjoy reading chapter 6. And there's sort of a copy of the first page. I'm not going to read it to you, but just notice that it was chapter 6, and the title of the chapter was Copulus. And that was the first time I had heard the word Copulus, was when I opened that book to that chapter. So why did Bert show me this book? I believe I mentioned statistics, and I've read every page in that book, and statistics appears only once in the entire book. So to answer the question, why did he show me the book, we need to discuss a little bit about, the functions that are in the title of the book, probabilistic metric spaces. And so here's a little bit of what I learned from the book and some papers that Bert had written with his students, his PhD students, and he shared those papers with me. And this is a little bit of what I learned. Informally, for you mathematicians, you'll know what a metric space is. It's a set, S, I'll call it, and a metric, call it D, that measures distances between points like P and Q. In a probabilistic metric space, we replace the actual distance, the distance between P and Q, with a distribution function whose values measure sort of the probability that a distance is less than or equal to, if you prefer, some real number x, usually a positive real number x. And the first difficulty in building this theory of probabilistic metric spaces is what's going to be the analog of the ordinary triangle inequality that says that the distance between 2 points, say P and R, is less than or equal to the sum of the distances from P to another point Q, and then the distance from Q back to R. And so what is going to be the corresponding relationship amongst the three corresponding cumulative distribution functions, F, and I'll subscript those with the points, then so there'd be F with the subscript PR, sub F sub PQ, and F sub QR. That was the first, and this was a major difficulty, and there were a number of attempts at coming up with an appropriate relationship. Most were failures. This is often the case in mathematics, until we finally get to one that was proposed by the Austrian mathematician Karl Menger, who had come to the United States in the 1930s. He was at the Illinois Institute of Technology and was Bert's advisor. And Menger proposed the expression in the little box on the slide, that the distance, the distribution function for F sub PR has to be at least as great as some function of the other two CDFs, cumulative distribution functions, and that function is denoted by T, and was called a triangle norm or a T norm. Triangle norm because it was being used in this triangle inequality. And it's going to be a mapping from the unit square to the unit interval, which satisfies 4 properties for all real numbers between 0 and 1 inclusive. The first one is sort of that, 1 is an identity for this function. The second one is sort of a symmetry condition. Maybe I can put my little hand up here to mention. Yeah, the second one is a symmetry condition. The third one, C here, basically says that the function is increasing in both variables. Whoops. And the third one here is kind of an associativity condition. If you want to go up to some sort of 3 variable functions, you have a couple of ways of doing it, sort of an associativity operation. And 2 of those conditions, A and C, and sometimes B, look like conditions. If you've studied copulas, you'll see there's corresponding conditions for copula functions. And the interesting condition of those 4 is the fourth one, associativity. And that was introduced in the sort of theory of these probabilistic metric spaces in order to extend the triangle inequality to a polygonal inequality that goes up beyond just 2 points, puts in more than one intermediate point. In chapter 5 in that book was entitled Associativity and concerns solutions to that equation up in item D, that this equation up here in item D is a functional equation. The unknown is the function. And what are the solutions? What are the functions that satisfy that equation? And so here are a few of those relevant results from those two chapters 5 and 6. This is an important theorem. It dates back to 1961. It says, I'll read it to you, let T be a T-norm that's continuous and strictly increasing on the two intervals mentioned. Then T has the following representation, very simple representation that T of AB involves some univariate functions, f and its inverse, evaluated at A and B. The function f is continuous and strictly increasing. F of 0 is infinite. F of 1 is 0. And the inverse is the inverse. And that's a very nice representation function. So it really sort of says what these T-norms have to look like. And so if you've studied calculus, you'll immediately notice that the T-norms are very, very close to an important family of copulas, the Archimedean Populace. And the name Archimedean Populace was stolen from T-norms. And the T-norm people called a T-norm Archimedean if sort of the diagonal, sort of T of AA, was always less than A, except at the endpoints. And in a couple of years after the theorem in the box, a fellow named Ling showed that the Archimedean T-norms, that the inverse is replaced actually by a pseudo-inverse, which appears in copula theory. And it's just a generalization of the inverse. You don't need to know any more than that about a pseudo-inverse at this point. So anyway, here are some examples from that 1961 paper written by Schweitzer and Schlar. And here are some examples of one-parameter families of T-norms. And here are 4 examples. I've used theta in each case for the parameter. And if you've worked at all with copulas, you'll recognize these for T-norm families as copula families. The difference between the family as a T-norm and the family as a copula has to do with the parameter theta. And on the right-hand side here, I've given some references that begin with F2, 4.2.6. Those are references to actual copula families in my book, copula families that have found application in a number of instances. In fact, they have names of those families. The first one there is often called the Joe copula, with the parameter being the one for copulas. Gumbel-Hugard copula. Number 3, I don't know of a name for that family. Number 4 is the Clayton. Actually, it's a subfamily of the one in my book, but it's the Clayton family of copulas, and so on. So I mentioned earlier that T-norms are quite close to copulas. In fact, some T-norms are copulas, but not all. And some copulas are T-norms, but not all. And in fact, the precise connection between T-norms and copulas occurs in 2 theorems. The first theorem tells us when is a T-norm a bivariate copula. T-norm is a bivariate copula if and only if it's 2 increasing. And the 2 increasing property is probably the most important sort of elementary property for copulas. And it says that if you have these 4 numbers in the unit interval, which I denoted as U1, U2, V1, V2, where they're ordered, U1's less than or equal to U2, V1's less than or equal to V2, then you have this sort of exclusion expression for copulas, which in terms of probability tells us that if we look at any rectangle within the unit square, the copula assigns non-negative mass to that rectangle in a very precise way. And that's an important property, and we'll see it a little later as well when we talk about other functions related to copulas, which are called quasi-copulas. And in the other direction, the theorem that tells us when a bivariate copula is a t-norm, the bivariate copula is a t-norm if and only if it's associative, if it satisfies that associativity property that was in the definition of t-norms. So a great many bivariate copulas are not associative. The associative ones are very special. They tend to be the Archimedean ones, and then some rather strange ones are constructed from the Archimedean. So I mentioned a little bit earlier that the word statistics appears once in this book, Probabilistic Metric Spaces, and it's in a reference to a couple of papers that Schweitzer and one of his PhD students, a fellow named Ned Wolf, wrote that came out of Ned's PhD thesis, and this is the statement from the book. It says, thus, much of the study of non-parametric or order statistics is intimately related to, indeed is often reducible to, the study of copulas. And that is an important sentence. When I saw that, I said, wow, this is special. In particular, in theorems of Fréchet and Schweitzer and Wolf, which express the fact that the surface for pi, that's the product copula. There's a copula which its value at numbers, say, x and y is just x times y. But the product copula lies midway between the surfaces for w and m. W and m are the extreme copulas. They come from the theorems of Fréchet that every copula lies between w and m. It's less than or equal to m and greater than or equal to w. So this product copula lies midway between the two extremes. It's natural to use any measure of distance between these surfaces as a measure of dependence for pairs of random variables. That's a direct quote from the book, and I think is one that, to me, has guided a lot of my work in sort of learning about how I can, measure these distances differently to come up with, say, different non-parametric measures of association. Well, prior to the 1980s, many, I'd say most, of the papers about copulas and their properties appeared in journals like the four that I've listed here. There's, I can't pronounce the Latin, Publicaciones Mathematicae de Brayson, that's out of Eastern Europe somewhere, the Cote Rendu, which is out of Paris, Cybernetica, Studia Mathematica, both out of Eastern Europe as well. And these journals, at least at that time, in fact, I would think today, are perhaps not generally read by statisticians.
The recording has started.
Oh, that's nice. Recording has started. Okay. And so it was sort of natural that statisticians were perhaps not as well aware of copulas at that time as they are now. But the second paper by Schweitzer and Wolf, it's off of Ned Wolf's PhD thesis, was actually published in the Annals of Statistics. And when I read that paper, I learned, amongst other things, these two expressions for population versions of Spearman's rho and Kendall's tau. And these are taken directly from that 1981 paper. Both of them involve double integrals over the unit square of different functions of the copula that corresponds to the distribution, or to the joint distribution of the two random variables. They're different, and that's why these two measures give you different numeric values, and so on. Well, to sort of conclude about the year I spent at UMass with Bert, I worked with Bert and another one of, well, I'd actually one of Abe Sklar's students, Jerry Frank, who was also at Illinois Tech when Bert was there, working with Menger, on a paper about bounds on the distribution function of a sum. And that was with Bert and Jerry, and then a paper that I worked on by myself was about the Frank family of copulas, which is one that Jerry created as a T-norm, actually, but a subfamily that were copulas, which included evaluating rho and tau using those expressions from the paper with Ned Wolf. And that sort of concludes sort of what I learned at that sort of year. It changed the direction of my life and really sort of set the stage for what I could do when I returned here to Lewis and Clark in the fall of '84. But the story doesn't end there. After that sabbatical year, it had been such a great year. I returned to UMass a couple of times. First time I returned was in the fall of '95 for a symposium that was celebrating Bert's retirement. I should point out that this was his retirement from teaching, but not his retirement from mathematics. And one afternoon at a coffee break that included some talks about copulas, one of the students, I think it was, asked what should he read to sort of learn the basics about copulas. And those of us who had done a little bit of research at that point mentioned some papers about copulas, some conference proceedings, and I foolishly, I guess, suggested that maybe the time was right for someone to write a monograph, sort of collect the relevant, ideas and theorems and applications into a monograph. And a colleague of mine, who I won't mention, said, "Good idea, Roger, why don't you write it?" And I was flattered by the suggestion, and I didn't do much at that time in the fall of '95. But a little later, I returned to UMass, and I finally, in the next sabbatical, I said, well, what I'll do on this sabbatical is I'll write that monograph. And I think it's an obvious fact that the primary reason that Professor Al-Adali gave me the kind invitation to give this talk is because I wrote that book, and many people have cited it. Not that it's that good of a book. I'm a little embarrassed right now. I wish I'd spent more time with it. I had no idea it'd become as popular as it has. But it was sort of the first one of its kind, and for many years the primary reference. And my heartfelt thanks to everyone who's found the book useful. It's embarrassing how many citations it has. I won't mention the number. It goes up every day. But I'm very flattered that people find it useful. And the story about how and when the book was written is in its preface. I won't go through that. And it's also in an interview that the editors of Dependence Modeling, which is a nice online journal that's publishing a lot of work about how copulas are used to model dependence in various fields. And you can find that interview at this website. And maybe I should just stay on this page, just in case. I can't see anybody out there. So if anyone is writing that address down, let me know when I can go to the next slide. Ahmed, are you there?
Yes, Professor.
Can I go to the next slide, or people want to write that address down? It's an interview. It's about 11-page article in that journal, and it's everything you wanted to know and probably didn't want to know about.
I'm already recording the presentation, so they could find this later.
Oh, okay. So it's a video recording, not just an audio recording. Huh?
Yes, it is video recording, Professor.
All right. I go to the next slide.
Okay, thank you. Thank you.
Okay, well, I mentioned earlier about quasi-calculus, and these have become important, and most of the work about quasi-copulas is in journals about fuzzy logic. And so quasi is a Latin prefix that means almost. And these things are sort of almost copulous. And occasionally some people label things as copulas, which aren't copulas, they're quasi-copulas. But let me tell you a little bit about the discovery of quasi-copulas, because this also occurred when I was back in Massachusetts. Back there for another sabbatical. This was 7 years after the first one. And when I was back there, Bert told me that he and fellow Claudia Alsina, who's in Barcelona, Spain, had been investigating the following situation in sort of, I guess it's probability theory or mathematical statistics, and I'll omit some of the details. But here was the problem. You have two random variables, x and y, with their corresponding distribution functions, f and g. Suppose that z is a random variable which is a function of x and y, and little psi is a binary operation on the set of distribution functions. Then psi could have two properties, to be derivable or induced pointwise. And here are those two properties. It's derivable if there exists a function z such that for every pair of distribution functions there exist random variables which have those distribution functions. Those are the distribution functions of the random variables. And psi of f and g is the distribution function of this function z. Very nice little property of this function psi. And psi is induced pointwise by a function cap psi, which goes from the unit square to the unit interval, such that for every pair of distribution functions in all real t, we have that psi of f and g evaluated at t is psi evaluated at f of t and g of t. It's induced pointwise by the points f of t and g of t. And so that's a bit abstract, so let me give you a couple of examples. The operation of convolution of distribution functions is derivable from addition of independent random variables, but it's not induced pointwise by the values of those distribution functions at a common point t. And operations such as and geometric means of distribution functions are induced pointwise, but they're not derivable. So the question that Bert and Claudia were investigating, what they wanted to answer is, are there binary operations, little psi, that are both derivable from a function z and induced by a pointwise, induced pointwise by a function cap psi? So that was the question. The answer is no. Well, there's no paper. If the answer is yes, then you go on and say exactly what they are. And the answer is yes. And there are trivial ones, which I won't mention. But the non-trivial ones come in two forms. And one form is, well, the function z is simply the maximum of x and y, and psi is a quasi-copula. And the other one is that z is the minimum of x and y, and psi is the dual of a quasi-copula. And when we talk about the dual of one of these functions, we talk about duals of t-norms, duals of copulas, duals of quasi-copulas. It's a quasi-copula Q that's related, as shown in this equation, that the dual is just some of the random variables minus the quasi-copula. And you can replace Q by a copula or a t-norm for duals of those functions. So that's a very nice thing, but the question is, well, Roger, what do you mean by quasi-copula? So let me continue with something about what a quasi-copula is. We were working on this paper, when I was working with Bert and Claudia on this paper, we thought these functions were going to be copulas, but we couldn't quite get the proof until we discussed that things that were almost copulas satisfies the property of that I mentioned above being induced pointwise. So what's a quasi-copula? It's almost a copula. So it has the same domain, the unit square, the same range, the unit interval, and it satisfies the same boundary conditions of a copula. And there they are, that when one of the arguments is 0, the value of the copula is 0. And when one of the arguments is 1, the value of the copula is the other argument. Those are the boundary conditions for copulas. Those are the boundary conditions for quasi-copulas. They are not the boundary conditions for T-norms. And the other condition for copula is the 2 increasing copula that I mentioned earlier. And for reference, here it is again. Okay, so rather than that 2 increasing condition, we replace it with these weaker properties down here, which are that Q is non-decreasing in each of its arguments, and that Q satisfies a Lipschitz condition. The 2 increasing condition for copulas say that copulas satisfy both of those, but if we replace the 2 increasing condition with the weaker condition, there are functions that satisfy non-decreasing in each argument and the Lipschitz property, but not the 2 increasing function. And those are the quasi-copulas. I believe that the first example of a proper quasi-copula, a function that is a quasi-copula but not a copula. I think I mentioned earlier, every copula is a quasi-copula, but the proper ones, the ones that are not copulas, do exist. And here is sort of the support diagram from the one in our paper from 1983, sort of saying where the probability mass lies within that unit square. And quasi-copulas, proper quasi-copulas, have places where the mass is negative. And, you know, I always have to put the word mass in quotes there because, you know, probabilities can't be negative, but these quasi-copulas have places where the function assigns a negative number to the quasi-copula. And so on this particular one, these 2 blue lines, which I'm outlining here, each have mass 2/3. So there's a total of 4/3 mass, too much, on the blue lines, but that's offset by this red line here, which has negative mass 1/3. And you can, you know, come up with the actual, you know, analytic expression for the values of the quasi-copula at every point within the square, but it's a bit complicated, so I won't do it. It's in my book, and it's also in that paper. Anyway, so quasi-copulas, one reason I'm mentioning them in this talk is the relationship that they have with copulas. And it turns out that if you have a set of quasi-copulas, a non-empty set of quasi-copulas, and you look at the point-wise least upper bound or supremum of the copulas in that set, or the quasi-copulas in that set, and the greatest lower bound or infimum, that those are quasi-copulas. The point-wise supremum and infimum of any set of quasi-copulas is a quasi-copula, and the same thing is true for copulas, that the point-wise supremum and infimum is a quasi-copula, not a copula necessarily. And hence the set of all quasi-copulas is a lattice theoretic completion of the set of copulas. So you think about sort of this lattice theoretic structure of a copulas, they all somehow lie below the Fréchet upper bound, which we call M, and above the Fréchet lower bound, which we call W. They lie in between those in some lattice theoretic, you know, something that looks like a lattice, but it's not a lattice until you throw in all the quasi-copulas as well. So that's really an important set because the copulas are sort of, you know, they live within that set of quasi-copulas. And when I did the second edition of the book, I added a section about quasi-copulas. And for a more recent, really nice survey by the Italian Carlo Sempi, take a look at chapter 13 in this recent Springer book, which is a collection of surveys about copulas and dependence models and their applications. published just 3 years ago, so it's pretty much up to date. Okay. I mentioned I wanted to talk a little bit about some trivia about copulas and sort of how they came to really be in the mainstream of certain areas in probability and areas in statistics. And for many years, there was a current index to statistics. I think it sort of died maybe 5 years ago. But when it was active, it indexed the entire contents of about 160 core journals in probability and statistics and related fields starting in 1975. And when they stopped publishing it maybe five years ago or so, there were 1,200 papers in there with the keyword copula. And the trivia is, well, when was the first, what was the first paper to use the keyword copula in the current index? And you might guess that it was one by Bert Schweitzer, and it's that one that I mentioned earlier with his student Ned Wolf, the paper I mentioned where they had the conversions of Spearman's rho and Kendall's tau in terms of copulas. The title of the paper is On Non-Parametric Measures of Dependence for Random Variables. And it was that paper in the Annals of Statistics. And that was from 1981, when the first, in the current index of statistics, when the paper finally, it did use the word copula as a keyword. That's the first occurrence of copula as a keyword. What was the first paper with the word copula in its title? And for this, to answer this question, I went to math reviews. And from the math reviews that are collected on the website MathSciNet, which I would be surprised if there's a mathematician on Earth that doesn't use that site at some point. And this was a paper from 1973, and it's a paper by Abe Sklar. And this paper was Random Variables, Joint Distribution Functions, and Copulas. And again, it's in this Eastern European, Czech journal Kybernetica. But notice who the reviewer was, Bert Schweitzer. So, I mean, these, one reason I sort of had that dedication early was not only did I learn about copulas from Bert Schweitzer, but he was really sort of fundamental in, what shall we say, getting, in creating doing the foundational work that has produced the theory of copulas as an important area in statistics. And today, I was putting this talk together. I went on the website and I said, well, how many papers are there with copula in the title? And MathSciNet gave me back over 2,100 papers are on that website with copula in the title. But that, I should point out, includes papers that use copula in the sense of logic. And so the third and final one of my little trivia things here, what's the subject classification code, the MST 2010 code for copulas? If you're doing a paper these days, the editor of the journal usually likes to see that little code. It begins usually for papers in copulas with the number 60 or 62. And what's the code for copulas in the 2010 MSC? And the answer to that is there wasn't one. And in the 2020 version, which just came out this year, there is a code for copulas. They just tack copulas onto 62H05, which is the one for sort of multivariate statistics. Multivariate probability distributions use this one, and now copulas is there as well. Well, let me kind of conclude with some good news and bad news. Out of being print for many years, the book Probabilistic Metric Spaces was republished by Dover. Dover is a good source for reasonably priced reprints of out-of-print books. And Bert and Abe, Bert Schweitzer and Abe Sklar, spent spent a good deal of time preparing this. They added over 30 pages of new material. And in chapter 6, the one on copulas, Bert Abe wrote the following: since the original publication of this book, there's been a phenomenal growth, not only of interest in copulas per se, but of their actual use in statistics and related areas. And what are some of those related areas? Well, I hate to do it, but sometimes I go to Wikipedia. Sometimes it's an authority, too often it's not. But when you type in the word copulas, you can get references to papers and applications in the following fields. So quantitative finance, civil engineering, reliability engineering, warranty data analysis, turbulent combustion, medicine, hydrology, climate and weather research, random vector generation. And I think, you know, they keep adding to that list. And it's any place using multivariate models for dependence, you know, anything beyond sort of, you know, independence, you know, any sort of dependence model for 2 or more random variables, more often than not are using Copulus. And although I hate to do it, I'm going to end with the bad news. Shouldn't do that. And the bad news really comes from a review that Bert wrote in 1995 about copulas in a review in the Mathematical Reviews. And this is I actually cut this out and highlighted it from the review on that website, on the MathSciNet website. Here's what Bert wrote. So in the paper under review, the author surveys some of the important properties of copulas and demonstrate ways in which they can be employed in courses on probability and mathematical statistics to characterize some dependence concepts for pairs of random variables, to obtain a geometric interpretation of the population version of a non-parametric correlation coefficient, and to illustrate how that coefficient measures dependence, and to facilitate the generation of counterexamples. And Bert concludes his review by writing, without doubt, the subject matter of this paper should and shall find its way into every standard text on mathematical statistics. The only question is, how long will it take? And when I was getting ready to actually think about this talk, I looked at several textbooks for the undergraduate course in probability and statistics, and the ones on my shelf and other department I looked at, not a single one of them mentioned copulas. And so to answer Bert's question, how long will it take? Well, it's been 25 years now, and we're still waiting. And my final comment for everyone in the audience is we still have work to do. This should not be just, relegated to graduate programs in mathematics and statistics and to graduate texts, but it should really be in textbooks that the undergraduates who will only get an undergraduate course and then go out to be a practitioner of statistics, they should be exposed to copulas and their role in dependence modeling. So I'm too old to do it. So all you young folks out there, we still have work to do. So I want to thank you very much for your kind attention, and I look forward to hearing more about the work that you're doing with the people, Professor Al-Aldali and his colleagues at your university, and let's keep in touch. So anyway, I want to thank you for your kind invitation, and I enjoyed and your attention and your attendance at the talk. Thank you very much.
Thank you very much, Professor.